Hello everyone. Today I am going to explain about the optimization of switching activity. Okay. In the previous discussion, I have explained the estimation of switching activity and we have calculated the equation for it. Now we have here the reduction of switching activity. Okay. So switching activity in CMOS digital integrated circuit can be reduced or optimized by using three methods. That is, first one is algorithmic optimization, and second one is architectural optimization, and third one is proper choice of logic topology or by circuit level optimization. Okay. So here I will consider the first one, that is nothing but algorithmic optimization. Algorithmic optimization depends heavily on the application and on the characteristics of the data, such as dynamic range, correlation, and statistics of the data transmission. Okay, so here algorithmic optimization means the name itself it is there. That is for the given task, which algorithm we have to use, to process that we have to select. Then only we can optimize this switching activity. So that is nothing but algorithmic optimization. Here we have next some of the techniques can be applied only for a specific applications such as digital signal processing and cannot be used for general purpose processing. Okay, so this is what one example what we have here. Okay, so whatever the design that is there, whatever the algorithm we have that is for the signal processing, we can use for that purpose only. We cannot use for other purposes. Okay, so that means what proper selection of algorithm is very important to reduce the switching activity by using algorithmic optimization. Okay, so that's what here we have. Some of the techniques can be applied only for a specific applications such as digital signal processing, DSP, and cannot be used for general purpose processing. Okay, so that means what DSP, digital signal processing process will be used for only that processing, signal processing purpose only. We cannot use for the general purpose. Okay, so that is one example we have. Like that, we have many examples here how we can select the algorithm, or how you can choose an algorithm to avoid the switching activity. Okay, or to reduce or to optimize the switching activity. So here another example we have here. Choosing a proper vector quantization algorithm can be chosen for minimum switching activity. Proper vector quantization algorithm is can be chosen for minimum switching activity. Also, the number of memory accesses, the number of multiplications, and the number of additions can be reduced about a factor of 30 if the differential three-search algorithm is used instead of the full search algorithm. Okay, so here I already told that the proper selection of algorithms is very important to reduce or to optimize the switching activity. So this is one example. Instead of using full search algorithm, if you use a differential tree search algorithm, we can reduce the switching activity here by a factor of 30. Right. Next one is here in our digital data representation. So if you go with the binary representation and gray code representation, which one is consist of less switching activities or less transitions? Okay, so here the gray code will have less transition as compared with the binary codes. That's why to represent our data, it is very important to represent with gray code. Okay, and at the same time we can also have signed number representation. Okay, so we will see one by one here. The representation of data can have a significant impact on switching activity at the system level. Okay, in applications where data bits change sequentially and are highly correlated, such as the address bits to access the instructions, the use of gray coding leads to a reduced number of transitions as compared to the simple binary coding. Okay, so if you observe here the binary coding and gray coding, the gray coding has less number of transitions, less number of changes, that is from 0 to 1 or 1 to 0 as compared with the binary coding. So whenever a less number of transitions is taking place, at that point the switching activity is also optimized. Okay, so here also for the data representation, the proper selection of representation is very, very important. If you compare the binary code and gray code, the binary code has more transitions, number transitions or bit transitions will take place as compared with the gray coding. So if you use the gray code, then we can optimize this switching activity as compared with the binary coding. Okay, next one is the use of sign magnitude representation instead of the conventional 2's complement representation for sign data. Okay, generally we will represent here the signed numbers. So signed numbers can be represented with two ways. One is what sign magnitude form. One is sign magnitude form, and another one is sign magnitude form, and second one is complement form. That means here generally we will use the 2's complement form. Okay, so these numbers, the signed magnitude numbers can be are signed numbers. Signed means here, unsigned means there is no sign will be represented before this binary representation. If assigned numbers means there will be a plus or minus will be there. Plus will be always the general representation itself. But if the negative sign is there, so we call that one as signed numbers. And those signed numbers, binary numbers, can be represented in two forms. One is signed magnitude form and another is complement form. That is 2's complement form. So signed magnitude means if you consider here, this is 0, 1, 0, 1, 0. This is of negative number, negative. So here we will represent here one sign bit. Here we will place sign bit. That is 1. If I place here, it is sign bit. Okay, so it will represent the signed number. This is the actually the negative number. So we will place another bit here. That bit will represent whether the given binary number is signed number or unsigned number. Okay, so that is here only one bit that will be changed as you represent with this negative number with our signed magnitude form. Okay, but if you consider the 2's complement form, first you have to, for a given number 1, 0, 1, 1, suppose it is the binary number we have. Okay, so for this one you have to represent the 2's complement form. So first you have to consider that 1's complement. Okay, so 1's complement is nothing but here we have to subtract all these binary, each binary number from 1. Okay, so therefore if you subtract this one, 1 minus 1 is 0, and here it is 0, and you will get 1, and it is 0. So this is the 1's complement. So to represent this negative number in 2's complement means again you have to calculate 2's complement. So how you can calculate the 2's complement? For this 1's complement, if you add 1, okay, if you add 1, so you will get the 2's complement. So it is 1, and here also it is 1 and 1, 0. Okay, that is 0 and 1, like that. If you add this 1 to this one, so you'll get the 2's complement. That means what here, how many process we have to consider, how many transitions we have to do here to represent a negative number or signed number in 2's complement is we have many steps, many transitions that has to take place as compared with the sign magnitude form and 2's complement form. Okay, here less number of transitions will be taking place in sign magnitude form. So to reduce or to optimize the switching activity, we will go for the signed bit representation, sign magnitude representation. So to represent a signed number. Okay, so that is what here, how the proper selection of data representation is also very important while optimizing the switching activities. Okay, so one is gray code here and one example, and another one is here we have is the sign magnitude representation. Okay, so the use of sign magnitude representation instead of the conventional 2's complementary representation for signed data. Okay, a change in sign will cause the transition of higher order bits in the 2's complement representation, whereas only one sign bit will be there in sign magnitude representation. Due to that, it will take less switching activities or less transitions. So therefore, while representing the data, that is signed numbers, we will prefer sign magnitude form to avoid the switching activities or to optimize the switching activities. Okay, so that's what here we have. The use of sign magnitude representation instead of the conventional 2's complement representation for signed data. Okay, so what we use, we will use the sign magnitude representation instead of the conventional 2's complement representation for signed data. Okay, so in signed magnitude, we will change only one representation, one sign bit we will assign for the signed number. But in 2's complement, what I have explained here is we have to consider more and more transitions. No transitions we have to consider. That's why the advantageous representation here to optimize the switching activity is sign magnitude representation only. Okay, so here, therefore, the switching activity can be reduced by using the sign magnitude representation in applications where the data sign changes are frequent. Okay, so where the data sign changes are frequent, at that point, it is very simple. If you change one bit, so that will be okay for the sign magnitude representation of sign numbers. But in conventional 2's complement, it is not the correct process. It is not a single transition that is taking place. There is more and more number of transitions, bit transitions will be takes place. So that's why here we will prefer the sign magnitude representation whenever there is a more frequent sign changes is there for the data. Okay, so that's what the difference between sign magnitude and 2's complement representation in the optimization of switching activities. Okay, so next we'll go with the glitch reduction. Okay, so this is about the algorithmic optimization. In this one, we have seen that the proper selection of algorithm is important to reduce the switching activity, and at the same time to reduce or to optimize the switching activity. So the very important thing is data representation. Okay, how the proper selection of process is required for the data representation, and for that we have given here two examples, that is gray code and binary code comparison, and at the same time sign magnitude representation and 2's complement representation. Okay, so next we'll go with the glitches. Okay, so reduction of glitches is also very important under architectural optimization of switching activity. So we are going to see about glitch reduction. Okay, so this glitch reduction is also a one of the process to avoid the to reduce the to optimize the switching activities. Okay, so here we have glitch reduction. So what is glitch and all those things we will see here. An important architectural level measures to reduce the switching activity is based on the delay balancing and the reduction of glitches. Okay, an important architectural level measure to reduce the switching activity is based on delay balancing and reduction of glitches. Okay, then what is glitch here? Okay, so we will see in multi-level logic circuits, the propagation delay from one logic block to the next can cause spurious signal transitions or glitches. As a result, we will get critical races or dynamic hazards. Okay, so due to these glitches, what happened is there will be a possibility of getting critical races or dynamic hazards. Okay, so how it will be, we will see here. So here again I am reading out this. In multi-level logic circuits, the propagation delay from one logic block to the next can cause spurious signal transitions or glitches. As a result, there will be a critical races or dynamic hazards will be obtained. Okay, so here I will explain this glitches reduction or glitches by taking this diagram. Okay, so here we have two NAND gates. First NAND gate output D is given to the second NAND gate input, and C is another input for this NAND gate. Now what happened here, if you observe this diagram, here A, B, C, all the three inputs are arriving in the same point, at the same point. But what happened to this D? Instead of arriving at this point, so it is arriving at this point. Okay, it is arriving at this point. Okay, so here applying of this D will be delayed by this much time. Okay, so due to that, what happened here is, so already A is applied and B is applied, and the output of D will be considered as the one input for this second NAND gate, and C will be applied at a time with AB. Okay, that means what, one input is already reached at the time of starting point of applying A and B. Okay, so if you consider here, 1 second. So if you consider here the inputs A and B and C, 3 will be reached at this point at the same time. Okay, but what about the D? D is nothing but the output of this NAND gate. So it will, to process this output D, it will take some time. The gate 1 will take some time. So, but already the C is reaches the second gate input, but here the D cannot develop or reach the second gate input at the same time of A and B and C. Okay, so due to that, what happened? We will get the wrong outputs. Okay, that's what here happening, right? So A and B and C are obtaining or reaching at the same time to their corresponding nodes, that is input nodes of gate 1 and gate 2. But the another input for the second NAND gate, D will be reach the input node after some time. Why it is getting some time means, here this gate has to process by taking these two inputs A and B, and it has to give the D output. Okay, so the D output will be given to this NAND gate. So here that the production of this D, or the reaching of this D at the input node of this NAND gate 2 will be delayed. Okay, due to the delay, what happened here, the final output what we have is cannot be get properly. Okay, so here it is reached at this point, all the three. Okay, but D will be reached at this point. So what happened here? So there will be a problem. So C is one input, this is what, higher value, and D we will get here is after this point we'll get some value. So if you consider NAND gate operation, here higher value and lower value, you will get the lower value. Okay, but what about this time? This time will be called as glitches. The output we cannot reach properly, so that and at the same time it will take the previous output. Okay, what we'll do is it will take the previous input. So this D will be late, that is generated from this NAND gate. So instead of that, at the starting point, C will be obtained already, but here the delay will be there. Because of the delay, what it will take, or this gate will take, is it will consider the previous input, whatever it may be, so that input it will take. That's why you will get glitches here. Okay, so that is one point we have to consider, how these glitches will be obtained. Okay, so because of the delay in the input to reach the input node, there will be a problem we will consider. We cannot get the proper output. So that's why that process is called as what, critical races or dynamic hazards. Okay, so that's what here I have considered this example, and I have explained about the glitch, how the glitches will be obtained. Due to that, what are the consequences that will be taking place is nothing but critical races or dynamic hazards. Okay, in general, if all the input signals of gate change simultaneously, no glitching occurs. A dynamic hazard or glitch can occur if the input signal changes at different time. That's what here, A and B and C are applied at the same time, but D will be delayed, so that because of that there will be a delay, or there will be a delay in that input. Due to that, the glitches will be obtained. Okay, A node can exhibit multiple transitions in a single clock cycle before settling to the correct logic level. In some cases, the signal glitches are only partial, that is, node voltage does not make a full transition between the ground and VDD levels. At even partial glitches can have a significant contribution to the dynamic power consumption. So this is what we have here. So to avoid this one, what we have to do, we have to reduce the delay to reach the input to the input node. Okay, so this is what we have glitch reduction, right? So here we can also have another representation, another circuit representation here. The same concept I will explain by taking another gate. Okay, so glitches occurs primarily due to the mismatch or the imbalance in the path lengths in the logic network. Okay, such a mismatch in path lengths results in a mismatch of signal timing with respect to the primary inputs. Okay, so if you consider here, this is one structure and this is another structure what we have. Both will give the same output. Okay, but it will give the glitches because, so if you consider this one, AB is there, this one is the XOR gate, so AB is there for us. AB will be applied and at the same time C and D will be also applied, suppose. So AB will be applied, they will process and it will give some output. That output is given to the second gate. And after that, the C and this output will process and that is given to the third gate. Okay, but A, B, C, D will be obtained at the same time, but there will be a delay in the another output, another input, that is for the two gates. Because of that, there will be a problem of glitches. That's what here that is taking place. Okay, so here instead of that, we can also construct, we can also make these changes to this gate. That means what, I will consider these two gates here and AB and CD, and the output of this one I will give to the another gate, so that the same output will be provided in both cases in A and B, but there will be a more possibility is there to obtain the glitches in the first circuit as compared with the second circuit. Why? Because here in the first circuit, so all the inputs cannot be obtained at the same time. Okay, cannot be obtained at the same time for the XOR gates. But here all the four inputs are obtaining at the same time, so that there will be a less possibility to obtain the glitches. Okay, so this is what we have. We can modify our, or we can change our structure to avoid this switching activity and at the same time this glitches. Okay, so that's what here we have. Glitches occurs primarily due to mismatch or imbalance in the path lengths in the logic network. Path length is nothing but in this one, if you compare these two, AB will be obtained at the same time and C is also obtained in the same time, but here the input for this gate cannot be obtained, so the path length is more here, but here the path length is very less. Due to that, the delays will be reduced, so the inputs can be reached properly to the input nodes. Because of that, we can avoid these glitches. Okay, so if you avoid these glitches, so we can also avoid the races and dynamic adjusts that are taking place. Okay, so this is the method to reduce the glitches. Okay, so here we have a 4 input parity XOR function using a chain structure, a tree structure which will reduce the glitches. So how this reduce means, due to this construction, so the path will be reduced, so that's why here the delay will be reduced, so that we can in this one the inputs reach in a proper time without delay, so we will get the proper outputs also, okay, without any glitches. So that's what here how you can reduce the glitches. Okay, so if all XOR gates have the same delay and 4 input signals arrive at the same time in figure A, the circuit will suffer from glitching due to the wide disparity between the arrival times of the input signals. So that's what here, these 4 will be arrives at the same time, but whatever the second inputs for gate 2 and gate 3 will be delayed. Okay, so that's why you will get the glitches in the first circuit, and we can avoid these glitches in the first circuit by considering or by rearranging the the architecture of this structure. Okay, so that's what here. In the network shown in figure, on the other hand, all the input arrival times are uniformly identical because the delay paths are balanced. Here it is not uniformly identical, but here all will be reaching at the same time. Okay, such a redesign can significantly reduce the glitches and gives a smaller overall propagation delay. Okay, so this is what glitch reduction. So here we'll have another method to reduce the switching activity. So that is nothing but gated clock signals. Okay, so here another effective design technique for reducing the switching activity in CMOS logic circuit is the use of conditional or gated clock signals. So what is it means? Conditional or gated signals means whenever we require the clock signal, for that signal only we will apply and we will use the same circuit uh, in the required time. Okay, so that's what here we have. Another effective design technique for reducing the switching activity in CMOS logic circuit is use of conditional or gated clock signals. Okay, so if certain logic blocks in a system are not immediately used during the current clock cycle, okay, so some logic blocks we cannot use at that time. We don't need we don't apply any clock pulse for that. Okay, so due to that we can reduce the power, right? So in certain logic, if certain logic blocks in a system are not immediately used during the current clock cycle, temporarily disabling the clock signal of these blocks will obviously saves the switching power. Okay, so that's what here unnecessary logic blocks we can, for unnecessary logic blocks we cannot apply any clock signal. Whenever they are required, we will apply the clock signal for them. Okay, but if certain logic blocks in the system are not immediately used during the current clock cycle, then we can disable the clock cycles for those circuits. Okay, after that, whenever we require, we will apply the clock signals for them. Due to that, we can reduce the switching power. Okay, so next one is the circuit compares the magnitudes of the two unsigned n-bit binary numbers and produce an output indicate which one is the larger. Okay, this is a comparator. Here we have A and B are two unsigned numbers, unsigned binary numbers. So we have to compare these two unsigned binary numbers. So to compare these things, we are having here, this is the complete comparator circuit, but another circuit is there, that is MSB comparator. Okay, so what it will do is here, so we are applying A and B bits for this gate and at the same time for this gate, for this register. So for this register only 2 bits we are applying, that is what the MSB bit, most significant bits. Okay, so that is 0. Suppose if you have 0 0 1 1 is there, and for B it is 1 1 0 0 is there. Okay, so we have to compare these two and we have to decide which one is the greater one, A is greater or B is greater. So first what it will do is, first it will send this significant bits, last 2 bits 0 0 to this 2-bit register, and at the same time 1 1. Okay, so at this point this registered output will be given to the MSB comparator. That MSB comparator will compare this MSB bits of A and MSB bits of B. Okay, so if 0 0 is present at the MSB bits and 1 1 is present for the second one B, so which one is greater here? 1 1 number is greater. So that will be decided by whom? The MSB comparator. So here the two MSB bits of A and B are given to the register, that is 2-bit register, and that output is given to the MSB comparator. So this MSB comparator will decide which one is greater by observing the MSB bits. So here 0 0 is there and 1 1 is there. 0 0 is present in A in the MSB bits and 1 1 is there in the B bit. Okay, B numbers. So which one is greater? This MSB will decide this B is greater one. Okay, so already the decision is taking place at this point. Okay, without going to this one, already the decision is taking place with this clock. Okay, because it is comparing the MSB bits, MSB comparator will compare and it will decide which one is greater. At that point, there is no need of applying the clock signal for this circuit or operating this circuit. So we can have here, we can reduce the more power by disabling the clock signal for these blocks, because already the decision is taken by this MSB comparator and the output we got. Okay, at that point of time, so we will avoid the, or we will disable the clock signal for this structure. So this type of clocking we can called as conditional clocking, or we can also say that gated clock signals. Okay, so that's what here we have. The circuit compares the magnitude of two unsigned n-bit binary numbers A and B and produces an output to indicate which one is larger. Okay, so in the conventional approach, all the input bits are first latched into the n-bit registers and subsequently applied to the comparator circuit in general conventional process. But here we are designing to optimize the switching activity. That's why we are going with the gated clock signals. So what is it means? Okay, so in this case, the two n-bit register arrays dissipate power in every clock cycle at if the most significant bits a(n-1) and b(n-1) of the two binary numbers are different from each other. Then the decision can be made by comparing the most significant bits. Okay, once here the decision is taken, so we cannot go with this block directly. We will decide at this point only. Whenever here there is no possibility of deciding which one is greater, so we will apply the gate signal. Until that, we will disable the gated clock signal or the clock signal for those things. Okay, like this we can reduce our power, that is dynamic power consumption. Okay, the two MSB bits are latched into a 2-bit register which is driven by the original system clock. At the same time, these 2 bits are applied to an XNOR gate and the output of XNOR is used to generate the gated clock signals with an AND gate. Okay, so that's what here how we can verify, right? The two MSB are different, 0 1 or 1 0. The XNOR produces a logic 0 at the output, disabling the clock signal of the lower order registers. Okay, in this case, a separate MSB comparator circuit is used to decide which one of the two numbers is larger. Okay, like that we are going to reduce the power supply. Okay, if the two MSB bits are identical, that is 0 0 or 1 1, the gated clock signal is applied to the lower order registers and the decision is made by the n-1 bit comparator circuits. Okay, so whatever it may be, here by considering this gated clock signals, we are going to reduce almost a 50% of the power consumption. Okay, by disabling the gated clock, by disabling the clock signal whenever they are not using. Okay, they are the logic blocks that are not using, right? So this type of method is called as gated clock signal or conditional clocking signal. Okay, so this is what here we have, how we can reduce the switching activity. Okay, thank you for watching. Subscribe our channel.